This time, let's look at a couple of questions on waves. The first one is on refraction. So take a look at this question, pause the video, and then have a look at my solutions. Okay, let's have a look at this. We've got light entering oil at 9 normal incidence here, and then it's hitting the oil-water boundary at 44 degrees incidence. The refractive indices of the materials are given here. The angle of refraction theta, if we write down Snell's law, we get n water sine theta in water is n oil sine theta in oil. If we put the values in, we get 1.33 times sine theta w, which is the angle we want, the angle in water, equals n oil 1.47 times sine 44, which is the angle of incidence, which in this case is the angle inside the oil. And that gives us actually 50.2, which is about 50 degrees. Always write a more precise answer to show. Don't just write 50. Always write 50.2, and then you can say, if you want, therefore, theta w is about 50 degrees. I'm going to write down my answers to part B and C, and then show you them now. Okay, there you go. You can see that I've made this ray that comes out parallel to the one that goes in originally, because the oil and the glass, we're told, have the same refractive index. So we're going to have symmetry here, and this angle here is going to be 44 degrees. You need to make sure you label that to get the mark. The reason why total internal reflection does not occur when we go from water to glass is that we're going from a less optically dense medium to a more optically dense medium. Another way of saying that is that glass has a higher refractive index than water. The critical angle for the boundary between the glass and the air, that's just a case of using the equation sine theta c equals n of the medium that you are entering divided by n of the medium you're leaving. It gives you 42.9 degrees. I write it to 3 significant figures because the refractive indices are written to 3 significant figures. We've got 1.47, therefore we're okay leaving that to 3 sig fig. Finally then, this last bit, on the figure above, complete the path of the ray after it strikes the boundary between the glass and the air. I'll give you 3, 2, 1. And if I move up here, you can see I've tried to indicate total internal reflection because the angle of incidence, 44 degrees, which this angle is here, using just using laws of angles, is greater than the critical angle we just calculated, which was 42.9 degrees. Therefore, we'll get total internal reflection. Okay, here's another question. This is on an optical fibre. So have a look at those questions, pause the video, and I will reveal my answers in 3, 2, 1. Okay, so you can see my answers, compare them to your own. Just a couple of things to note. Remember, the definition of refractive index is the speed of light in a vacuum divided by the speed of light in the medium. And also, if you ever forget the equation to work out the critical angle, always remember that the medium with the largest refractive index goes on the bottom, because then that means that the fraction, which is the ratio of the refractive indices, is less than 1, which must be the case if we're going to get an answer here for theta c. Remember, sine can only go between -1 and up to 1. So that tells you which way round the refractive indices have to go on that relationship. Anyway, have a go at D and E. Pause the video, and then I'll show my answers in 3, 2, 1. What to say about these? Well, you'll notice that we know that this angle is 80.5 because we've got an angle of refraction here of exactly 90 degrees. So that's the critical angle, 80.5, which we worked out here. Working backwards, because this is a right angle triangle, this angle here is going to be 90 minus 80.5, so 9.5 degrees, which we can then use with Snell's law to work out this angle here, which is what I've done. You can go away and look at that. E, why do we get a pulse that is flattened and broadened? Well, the first reason is energy loss due to absorption and or attenuation within the fibre as the light passes through a material. The second element, the broadening of this pulse, is due to multipath dispersion, which is to do with the fact that different rays, and I'm going to ruin this diagram now, different rays travel different distances through the fibre. So you can have one which maybe does 2 total internal reflections on this diagram, one which goes straight, and one which does something in between. So they all travel different distances, so they take slightly different times to travel, which means that a pulse which is originally quite sharply resolved in time ends up becoming smeared because of these multiple paths that the light can take. So that is the reason for the multipath dispersion. Okay, final question. Diffraction grating. Have a go at parts A and B by pausing the video now. My answer's in 3, 2, 1. Okay, so the main use of a spectrometer diffraction grating like this is to analyse the light coming from a sample to determine its elemental composition or chemical composition. So the one that occurs to me first is analysis of light from stars, either to determine their composition, but you can also measure the redshift of the spectral lines to determine something about the motion or the rotation of the star. You can also use this more generally for any chemical sample. So in a lab on Earth, for instance. B part 1, the key part here is a spectrum is not observed until, because obviously we get the central maximum, but then the first fringe we'll see will be the first order. So it's first order. In the middle, if we had white light coming through here, all of the wavelengths would constructively interfere in the middle here at A, whereas then as we get further out from the centre, we're going to get the separation of the wavelengths. And so at B, typically we'll see a spectrum, separation of different wavelengths of light. Moving down, let's have a look at C. And let me do this real time. The angle of diffraction at the centre of the observed beam B above is 51 degrees, and the grating has 1,480 lines per millimetre. Now the equation, which we're interested in, is d sine theta equals n lambda. We've been told, or we've ascertained already, that this is the first order. So first of all, let's work out d in fact. So d is going to be 1 millimetre over 1480, which is 6.76 times 10 to the minus 4 metres. Actually, no, millimetres, remember, because it's per millimetre. So in fact, that means it's going to be 6.76 times 10 to the minus 7 metres. So then if I put that into my equation, 6.76 times 10 to the minus 7 times sine of 51, that's going to give me my wavelength, which will be 5.25 times 10 to the minus 7 metres, or 525 nanometres. D, determined by calculation whether any more orders could be observed at the wavelength calculated in part C. So what we want to do here, again, we've got n lambda equals d sine theta, and we want to work out what n is for our given wavelength, 5.25 times 10 to the minus 7, with the same value of d. And we want to set the maximum angle that we can possibly get is 90 degrees, isn't it, from the centre for a visible order. So we've got that, sine of 90 of course equals 1. So what we're interested in seeing is what the value of n, 7.6 times 10 to the minus 7 over 5.25 times 10 to the minus 7 is. And that is quite clearly less than 2. It's about 1.29. Which means that are we going to see any more orders? No, we're not. No, since n is less than, not greater than, less than 2. Done.